For those of you guys just joining us, the recorder's kind of stopped working, so did the webcam. But here are the answers. Pause them if you need them to the evens. We've already checked. We've already graded. And now we're looking at the ones in the 70s because we didn't like them in homework. For those of you guys who are out in the audience, a.k.a. all of you, Alec, please stop. We're going to go ahead and check out, starting with number 71 and then going to the other 70s that we don't like. However, before we get too much into this, we do have, guys, please stop talking. Nothing else, have a little bit of compassion, although you should have some respect as well. 71 is like 72. So 72 I did really quickly at the end of yesterday, and some of you guys might not have realized how easy this could be, because remember, I told you the concept got heavy, the concept got hard, but the application was meant to be fairly easy. If you guys realize 72 was just like 71, I'll pull it up in a second. All I had to do was the dot product of the two vectors. The one that shows the distance that's moved, and then the one that shows the force. Now, if I have this force guy, which was the vector force they told me was V, I already have his components from his linear combination. But why am I subtracting for the other guy?
Because it's negative.
Yeah, they didn't give me the components. They gave me the beginning and ending points. So I had to do x, final x minus initial x, final y minus initial y. So I had to get his components to be -4, 2. But if you had gotten this at the end of yesterday, all you had to do to find work for this one was just the dot product, which is -2 times -4, +8, and 3 times 2 is 6. It was as easy as that. Now let's check out number 71. Maybe it's that easy and maybe it's not. Oh, but check it. Can I make this guy into a vector component also?
Yes.
Yeah. 4 minus 0, 7 minus 0. I can get him into components too. And then I can do the dot product with the force vector. So all you needed was, when I wrote down at the end of yesterday, being like just the dot product. So 4 times 1 is 4, plus 7 times 4 is 28. That's the dot product, right? X is multiplied plus y is multiplied. Jade.
What did you do combine P and Q?
Oh, P and Q, that's when a vector is defined by its initial point and its final point. And so whenever we need to get a PQ, because we don't have it yet in components, we can do, what would it be, the latter point minus the initial point. So we would do, some people would say XF minus XI, final minus initial. You could also think about it as your Q1 minus your P1 if you're doing like his X minus his X. And then we would do the final Y minus the initial Y, which would be like Q2 minus P2, if that helps as far as having a little baby focus. So that was 71. I lost whatever other numbers you said. What were the other 70s? 79 and 76. Okay. Let's go peek at 76, which is a little bit different in the sense of what it's been giving, or what it's given you. It doesn't give it to you the same way as 71 and 72. It's talking about a sport utility vehicle rolling down the hill. I have his gross weight of 5,400 pounds. I have an angle of 10 degrees, but remember, we don't care so much about that one as we care how that translates in this guy down here. There we go. That's that little inclined triangle from section 6.3. We have a gross weight of 5,400 pounds. Weight combines with gravity. That's this guy over here. So that's 5,400, which is technically our hypotenuse. A slope of 10 degrees. Remember, that can get thrown into our triangle up there. So there's 10 degrees. The only force to overcome is the force of gravity. So find the force required to keep the vehicle rolling down the hill. Well, that's cool. I'm just looking for to keep it from rolling down the hill. That's the one that the brakes are having to exert to keep it from falling. So that's this X1. That's opposite and hypotenuse. All we have to use is sine.
Is that right triangle?
Mm-hmm. Back from the 6.3 triangle, something on a hill. Yeah. And then for the next one, it says that's what X is. The next one says find the force perpendicular to the hill. That's this guy over here. So I'm just going to use adjacent over hypotenuse. Remember, this is the one in section 5.3 that I said the concept is hard, but with the picture, it's easy. The right triangle. So we need to have that right triangle to be able to do it quickly. Does that kind of make sense? Then you guys, I can assume you can multiply by 5,400 and then know x and y. Is that good? Okay. That was, now, in the answer key, that might have looked way more complicated. Like, what? But was it that bad?
They use another formula.
Well, they actually used, well, yeah, they used the projection, but they also used Pythagorean theorem, because once you know two sides, you can go ahead and find the next one. So if you know hypotenuse and opposite, you could have technically done a squared plus b squared is c squared. They use Pythagorean theorem, but both ways technically work. I'll play this right now. What was that last one? 79? I need to pull the book down. So. There it is. Hi, kiddo. Force of 45 pounds exerted at an angle of 30 degrees with the horizontal. So I have a horizontal going this way. I have 30 degrees going that way. I have a force that's being exerted going this way with 45 pounds. Is required to slide a table across the floor. Determine the work. I need force times distance. I need a force vector. I need this force vector. And as we talked about yesterday, projection says, how does the force or the vector that's exerted at the angle, how does that project down onto? There is that snazzy big old formula. But the nice thing is in this case is that really I'm able to, because the table is sliding this whole amount, this bigger amount. But we can make a distance vector if we wanted to. If that helps you guys, we could say that the distance vector is equal to, we're moving 20 feet horizontally and no feet vertically. That actually makes our lives a lot easier. We could say 20 feet horizontally, 0 feet vertically, or we could even kind of just say 20. And then with the force vector, we could go ahead and actually make him a vector with his, getting his components. We could do 45 cosine, not 45, sorry, cosine 30 and 45 sine 30. So we could technically do the dot product like you guys just saw me do in number 71 and 72. The other way, though, is that you could just be like, I just need the force that's in line with the table moving. I just need this guy. So you could almost even just avoid the dot product altogether and having to write all the components because it's not really even a component-ish question. You'd be like, I just need you. I just need this projected force, and then multiply that by the distance. And so the other way of doing it is that you could say, okay, I just need you, which is adjacent over hypotenuse, which is cosine. So I could do 45 cosine of 30. And then I could say, well, that's my force, and that's the force in line with the table. So I could actually just do that times 20, and that would be my force times my distance. And either one should work. And actually, if you guys notice, isn't that exactly what's going to happen with the dot product? Horizontal times horizontal plus 0. So it ends up, because it's that nice, unlike the ones we saw yesterday that were tilted, so you had a vector acting at another vector, and neither of them were horizontal. Since this one is horizontal, and anything that you're going to see on the test would be horizontal too, you don't even need to know that projection formula. You're not even going to need to use that projection formula. You're going to be able to either do a dot product like 71, 72, or you're going to be able to either solve your right triangle or just put them in components and do a dot product. Either way works. Because it's nice and simple since it's on the horizontal. And I realized a lot of you guys, we were doing that complicated one at the end of yesterday with, I can show it to you, you probably don't know what I'm talking about. we were doing this hard one, how U was being projected onto V, and it was like another line other than the horizontal. But this one, see how it's just the horizontal? Makes life so much easier. We can just do a simple right triangle with components, and then we got it. A simple right triangle with components, and then we got it. All right. I think that pretty much covers all the questions that you guys had for section 6.4, at least that you brought up. Let's go ahead and I also gave you guys some hints, like how projection, like using the long form of projection and the tricky tilted form of projection will not be on the test at all. And how any work that's done could be simplified down to a dot product if you could write it in components. Or to be honest, like a right triangle like the one you just saw. But let's get into our complex number reading. Okay, so I think I have this so that I can see it better this way, although that's kind of awkward. Can we see it a little bit better? Some of you guys were asking at the very beginning, like, what's A plus BI? That's the old-fashioned complex number, like when we covered complex numbers in chapter 3. Yeah. Chapter 2. It was chapter 2 because we were having to find imaginary zeros of quadratics. So we did a quick timeout in chapter 2 with complex numbers. And we saw that complex numbers aren't just like 2i, but it could be like a real number plus or minus that 2i. We just never talked about how technically there's a graphical representation of complex numbers. And you might be like, really excited, like, oh, we're going to see what imaginary numbers look like. Not really. They've just taken a normal XY plane and they've said, okay, for imaginary numbers, we can show them by talking about how like the x-axis is the real part and the imaginary axis, the y-axis, is like the imaginary part. I probably shouldn't say even x and y though, because even imaginary numbers, they don't use x's and y's. They use a's and b's. So we can say like the a-axis and the b-axis. So anytime you see like an A and a B, which, hold on, for vectors was like horizontal, vertical, right? A, B. Nice. That's for trig too. I can use the A component or the first part of my complex number to go out on the A axis at positive 3. The B component can go down negative 2. This is actual, and we actually connect it. This is a graphical representation of 3 minus 2i, because you have your 3 and you have your minus 2. It's not an ordered pair per se, but it's more of just kind of like another application of an xy axis for imaginary numbers. So we relabel things, we change them up a little bit. This is not a real xy. This is a complex plane where we have real numbers and imaginary numbers. We can graph over the real, down the imaginary, or I should say the imaginary is up or down, but this one's negative. Which might make a little more sense as to why this formula is what it is, though. If I want, I know, it's a single line, because technically this is a number. It's a number. It's a complex number, but it's a number. Absolute value of numbers is the magnitude of the number. What's the absolute value of negative 4? That's how much. There's 4 in there, right? It's a distance of 4 just to the left of 0. Or absolute value of 10 is 10 because it's a distance of 10 from 0. So we're used to absolute value being magnitude. We just haven't really seen it much lately. And this is a number, so it's not a double line, not a vector magnitude. It's like a number magnitude. But if you see that if this is a complex number, then maybe it makes sense that the how muchness of this would be that Pythagorean theorem, because you still have like an A and a B kind of like vectors. That's why we're kind of talking about it. The trig form of a complex number building into that. The graphical form of a complex number, it has a lot to do with vectors because it's still kind of using right triangles and horizontal vertical components. So guys, what quadrant would this guy be in if I was to graph this complex number? Yeah, it'd be like this one right up here, except it's going to be over 5 and down 12. But what would his magnitude be?
That would be 12 absolute value. 5 to 12 absolute value. Yeah,
but what would that equal? You have to think think about absolute value as magnitude, and magnitude of complex numbers, you have to think magnitude of vectors. Do you see it? You're going to have to do your 5 squared plus your negative 12 squared. So it's going to end up being 13, which is weird. How can the magnitude of a complex number be real? But it is. So the formula is not new, just the application is new. It's magnitude of a complex number instead of magnitude of a vector, but we use the exact same formula if we can just realize that there are horizontal and vertical components of complex numbers also. Same formula, just a little bit different application. Now you guys also have filled in the next page of notes. I could try to zoom in on that top because I know that picture is kind of light anyway. So if we zoom in on that top one, you guys can see they've graphed a complex number in the second quadrant, which would mean that it would have been a negative A and a positive B, right? A is that real component of the complex number, right? But we can also think about it as the horizontal if we're trying to compare it to vectors. B is the imaginary, but we can also think about it as the vertical component if we're trying to kind of keep it in line with vectors. R is just our radius, thinking kind of like a unit circle-ish. We're going out. And theta is just, we can call it the direction. So up until this point, you've only seen complex numbers in their standard form, their A plus BI form, their horizontal vertical form. But kind of like with vectors that don't just have to be said in their components, but also in their direction magnitude, we can kind of talk about complex numbers differently also. And so they brought up this trigonometric form, which says, you know what, kind of like vectors. A can come from magnitude, which in this case, the magnitude is the length, which we can call R, cosine theta, and B can come from magnitude sine theta. See, we're using a lot of the same formulas. But if you were to plug in R cosine theta plus R sine theta times I, well, first of all, sine theta times I is going to look real weird. Bless you. That's going to look real weird, real awkward. So instead of writing it like that, we actually write the I in front. That way it's clear, it's imaginary, it's an imaginary number. The I is right there. And we can say there's an R in common, so we can factor out the common R that comes in front. And actually, this whole notation, even though it's really just the A plus BI, but with the R's and thetas plugged in, there is a shortcut for this that some people have used in old pre-cal books that I've used in the past. They call it cis theta. Because it's R times cosine theta plus I sine theta. It's like a shortcut of what's actually in there. Our book doesn't use it, but I mean, it is a lot shorter than actually writing cosine theta plus I sine theta over and over and over again. And if you guys remember with T-proofs and stuff, as soon as we have trig, we can change, we can manipulate, we can square, we can plug in, we can transform. So reasons being, I mean, they aren't a total number of reasons, but just for you guys to realize, if I can write like a standard number in a trig form, maybe if I couldn't do something here, maybe I can do something there. At least in calculus, there's something where we can take functions that don't have trig, and we can write them with trig. We kind of bring trig into the picture to be able to move it and change it and make it something that we can use, because the original guide we couldn't use. Anyway, kind of introducing a few things as to why they might want complex numbers, not just the standard way, but also they might want some trig in there. But how do you actually do that? Well, let's look down below. How do you go from standard form to trig form, and how do you go from trig form back? Well, this is standard form, A plus BI. So I could say that my A is 1, my B is negative root 3. Kind of like vector components, if that kind of helps. If that kind of helps, maybe you guys, if you know you're trying to plug into R and then cosine theta plus I sine theta, maybe you can remember that when we had A's and B's before and we wanted magnitudes, we would always use our square root formula. I guess we don't need R squared. So we could just do that a squared plus b squared, which would be 1 plus 3 is 4, and square root of 4 is 2. So I could actually start plugging in, being like, well, I know my r is 2. That's how long my vector is. If I was to draw this guy, which this guy would go in the fourth quadrant also, over 1 and down with root 3, which is 1 point something. So my r would use that 1 and use that root 3 little Pythagorean theorem, and I get that 2 as my r. But then I also want my angle. How did we find angles with vectors, guys, if we didn't have them?
Cosine.
Nope. Not that one. Why am I starting to write tangent?
Oh. You can use that negative.
Adjacent.
Yeah, because I have opposite and I have adjacent. I need to use tangent. So I can do tangent inverse of negative root 3 over 1. Now you guys, I already told you you're going to be able to have your calculator this entire chapter, this entire test. So you could just throw that in degree mode. Sorry, that negative 1 looks awful. You could just throw it in your degree mode. But I actually know that tangent is root 3. That's square root 3 over 3. 1 square root of 3. 60 degrees. But why am I going to, even though this would be 60 degrees in my calculator, why am I going to come up here and write it as 300 degrees?
For the reference.
60 is the reference angle, but what quadrant am I in based on this picture? Fourth quadrant. I'm in the fourth quadrant. And actually, even though you're like, wait, I know that, I can't, nope, stop. The point of trig form is that you've brought trig functions in where they weren't before. It's just a snazzy way of writing a complex number in a different form with different values. Instead of just plain old-fashioned numeric values, we're using trig values. But the cool thing is, if I just said we're allowed to use our calculator, and if I just said, well, some of you might try plugging that into your calculator, but you would end up right back here. Hold on, what do you think you're supposed to do for this problem then? Condense it, yeah. This is kind of like the expanded form to include trig. Going to standard form is condensing it. It's like, oh, I really just say what is cosine of 135? And I really just say what is sine of 135? Now, I'm lazy. I don't want to get out my calculator. I know 135 is a 45 in this quadrant, so I actually know that my sine. I'm lazy. But you guys, technically, could plug this into your calculator. I'm just like, where's my calculator? I don't know. Somewhere. Is it in degree mode? I don't know. I was probably doing calculus last. So I'm just going to go ahead and keep it in this form. But you guys could have gotten decimals. And this is standard form. So standard form is just like, plug and chug. What's 5 times cosine 135? What's 5 times sine of 135? Okay, put those numbers and I got them. Put those numbers and I got them. But the trig form says, okay, I have these basic numbers. Can I put the trig in? So I kind of have to use some formulas for going to trig form. But returning from trig form, it's just like a plug and chug. If that helps you guys, you might want to write in like number 13, use formulas to get to trig form. But for like number 20, just plug in. You're just solving. All you got to do is just plug in and simplify. So that's going back and forth from trig form to standard form. And so once we have these complex numbers in trig form, one application. We're going to stop here. There's technically a de Moivre's theorem that has to do with raising complex numbers to powers, like squaring it and cubing it and fourth powering it, which to be honest is probably the most practical thing of the entire section. Trig form's practical, but once you get it into trig form, because of trig properties, and it would be so hard and it would take a long time, like a whole extra day for me to show you why. But long story short, if I was to multiply these two together, if I was to FOIL them with cosine squares and I sine squares and 2 cosine sine thetas, I could actually get back to these sum and difference formulas. I would have to come backwards in. But the nice thing is I don't have to go FOILing complex numbers to multiply them. I can actually just kind of memorize a few different properties that will always work for trig forms of complex numbers to help me perform operations on them. And so this is the last page of notes for today. I'm just going to show you 2 examples of how to use the formulas. The formulas say, if you can get the complex number in trig form to multiply or to divide complex numbers, all I have to remember is the r's just behave like the numbers themselves. Because the r's are just numbers themselves. No big deal. The r's just behave like the operation you're doing. And so in this one, if I'm trying to multiply, if this is Z1 and this is Z2, if I'm trying to multiply them, I can say 2 times 6 is 12, and I'm like, yeah. But these binomials, I'd have to FOIL them and then figure out how to simplify them in order to solve 4. Or I could just say, you know what, there's a cool property that says multiplication, like multiplying like bases, you add the powers. Multiplication, you add the thetas. Now you can skip all the FOILing work. Whereas division, if I was dividing Z1 by Z2, the numbers, no big deal, 5 divided by 4. But I could do division. When I divide like bases, I subtract. Just a silly way of remembering. I can subtract the angles. In some ways, it saves a lot of work. And ultimately, in raising them to powers, because if I were to cube a binomial, or 4th power, 5th power, man, it could get really gross really fast. And so de Moivre's theorem is the most practical, but that's the one that won't be on the test for sake of time. 1/4, and that'd be 3/12. And 1/12 would be 4/12. I think we end up with cosine pi over 3 plus I sine pi over 3. If they wanted standard form, no big deal. I could just plug it in. If they want trig form, I'm done. And this one, if they want standard form, no big deal. I could plug into my calculator whatever cosine is of, I don't even know, what is that, 2.2? I don't know, but I guess my calculator would. If they wanted standard form, I would just plug it in. If they want trig form, I would just leave it. But anyway, we didn't get to that de Moivre's theorem, but that's okay. It's just a little bit more advanced, and it's how to square root, cube root complex numbers. If complex numbers have an actual application, well, man, it'd be nice to have a way to cube root or square it or cube it without having to just look at the a plus bi. That's where trig form comes in handy. That's okay. That's okay. We saw a peek at them, and a peek at how vectors kind of applies in triangles. I think that's it. I'll go ahead and put a comment on your homework about the ones you get to skip at the end if I do have any de Moivre's. I'll look at it right now. Bye. If you guys talk to Cassie or Ella or Claire, tell them I hope they get feeling better.